One of the things that we strive to do as humans is to explain the world around us. So we have different models and different theories that we've developed over time to try to help explain what we see and what we experience. So as we were trying to understand matter and the atom, we came from a very nebulous look at things. Back in, ancient Greece, they had this air, earth, water, and fire. So those were the four elements. And then if you combine them, like air and fire combined together gave you something that was hot. Fire and earth gave you something that was dry. Air and water gave you wetness. So we strove to make these explanations with what we knew. Well, as we've progressed, we've been able to probe a little deeper and figure out a little bit more. So this guy Democritus in 470 to 370 BC is when this person lived. He proposed the idea of atoms, these tiny little things that made up everything. And then we needed to understand what an atom was and all the pieces and parts that went into an atom, and that's where Dalton came in. So Dalton is the one that started to propose what became our modern atomic theory. Right now, Dalton's atomic theory had some basic principles to it, though as we'll see, these basic principles, most of them still ring true, but there's one principle that we're going to learn as we learn more about atoms didn't hold completely true. So let's take a look at these. Okay, so atomic theory, elements, matter, composed of small indivisible particles called atoms. All right. Atoms of a given element are identical in mass and behavior. Atoms of different elements differ in mass and behavior. Chemical combination of elements to make different substances occurs when we join things together in these small whole number ratios. So this is important, whole number. I cannot react half of an atom, so things have to be in whole numbers. Okay, and then our chemical reactions, they just rearrange the way things are combined. We don't actually change the atoms themselves. If I want to start mess with atoms themselves and change, something fundamental about an atom, I need, a particle accelerator, and I need to do nuclear chemistry, not regular benchtop chemistry. All right, so if you've had some chemistry before, when you read through this list, you might be able to pick out the one piece that falls apart just a little bit. Think about this for a second. Those of you that have had chemistry. All right, so for those of you that haven't, the one that falls apart just a little bit is the second one, where it says atoms of a given element are identical in mass and behavior. And so what falls apart is this in mass portion of it. And we'll talk about why that is as we explore the structure of an atom. So if I have an atom of a given element, the behavior is going to stay the same, but we're going to introduce a concept of something called isotopes as we talk about all of this, where we'll learn that we can have a sample of an element and the atoms can differ in their mass. Now, there were things that absolutely supported a lot of Dalton's theory. So when we talk about, we've got our various different chemical combinations and we have things joining together in small whole number ratios, there's some things that we can start to put together. So we end up with this first thing, the law of constant composition. So what this is saying is if I have a substance, it doesn't matter where I get that substance from or how it was made, doesn't matter. It's all going to have the same composition. So if I have something like water, water is always H2O. Okay, and it's not going to matter if I go down to Lake Murray and I scoop a sample of water, or I drive down to the beach and I scoop a sample of water. Once I filter out all the other impurities, the water is just the water. Water is always going to be H2O. I can collect rainwater in my backyard. I can fly to the other side of the world, and I'm always going to get H2O. Okay? Water is always going to be formed from a couple of oxygen atoms, some hydrogen atoms, and getting our H2O, 2 water molecules. Okay, so constant composition. If we have a substance, it's always going to have the same composition. Now we have another law, this multiple proportions, okay? So when things combine, they can combine in different ratios. Now the ratios have to come down to whole numbers. So I have a couple of examples here, 2 different carbon oxides, okay? So I have an amount of carbon per 100 grams of the compound and an amount of oxygen per 100 grams of the compound. What I'm going to do is I'm going to take these numbers and I'm going to divide them by some numbers I find on the periodic table. All right, so if I start off with carbon oxide 1, I have 57.1 grams of oxygen for every 100 grams of the compound. So I'm going to take my 57.1 divided by this number I find on oxygen on the periodic table, 16. And I'm going to get 3.57. I'm going to do the same thing for the carbon, 42.9. I'm going to divide by the 12.01 on the periodic table, and I'm going to get 3.57, okay? There's a little bit more technical process to explain what I'm doing here, but for the sake of what we're doing, I'm just going to show you that we get these whole numbers. Now, 3.57 is not a whole number. So what I do is I have to divide both of my answers by the lowest number. Well, 3.57 and 3.57 is exactly the same, so I get a 1-to-1 ratio. So my carbon oxide 1 ends up being oh, I hit the wrong color, just a moment. My carbon oxide 1 ends up being CO. Now I can do the same thing for the second carbon oxide. I can take my 72.7 divided by 16, and I'm going to get 4.54. I'll take my 27.3 divided by 12.01, and I'm going to get 2.27. Now, this is not 1-to-1. So if I divide by the lower number, so if I take 2.27 and I take 4.54 divided by 2.27, and 2.27 divided by 2.27, I get a 2-to-1 ratio. Okay? The 2.27 had to do with the carbon, so that's the 1, and the 2 is the oxygen, and so I get CO2. Okay, so we get these whole number ratios that things combine by. Okay, so whole numbers. Can't have half of an atom. Have to have a whole number.